Okay. Well, yeah. Thanks for joining. Thanks, Luigi, for the introduction. It is a cooperation stuff, so you should give him some credit. Thanks for joining. This will be the workshop about multi-hazard modeling with OpenLISEM, which is an open source free software that tries to integrate different hazardous processes into one modeling suite. Today it is a workshop, so hopefully we'll get a bit practical. You get to run the software, get some hands-on experience. We'll see where it goes. It's a bit flexible, so after I did an introduction and showed you some of the stuff, you can have a say in what we'll do next, whether I'll talk some more or whether you want to actually try stuff out. Okay, so as a main point, what we saw was in the past years there were some hurricanes that went over a few Caribbean islands, particularly the smaller ones here. You have there Grenada, Dominica, St. Lucia, small islands, 30 by 60 kilometers, maybe 100,000 inhabitants. And these hurricanes tend to cause a lot of damage. This is an example after Hurricane Erica on Dominica. So what you see here is a lot of shallow landslides, debris flows rushing down. Well, okay, we want to try to predict this, to model this, to understand this better. But that's a hard exercise, because what is actually happening here? Typically, if you want to model this stuff, you go to a model that does either debris flows or slope stability, or a model that does flooding. But in this case, it's usually more at the same time. So in the schematic view, you have a catchment area, a river going down, coastline, some elements at risk there. So you have a flood hazard. You might have a coastal hazard, some storm surge or tsunami stuff. You might have a slope failure and landslide hazard. And these can all be analyzed independently, but what happens in reality is that they might happen at the same time, because they share a common trigger. In this case, we're talking about intense precipitation. Typically, intense precipitation triggers flooding, storm surges, it triggers landslides, slope failures, debris flows. So we set out to say, what can we say about multi-hazard simulations? What can we do there? So for us, our niche at the moment is weather events. They trigger a variety of hazardous processes. These processes interact. So, for example, the landslide can be diluted by runoff water or enter flooding, and then all the debris spreads to a larger area. You might say that a blocking of a channel can increase flood area. Bridges can get much more impact pressure because of all the debris in the water. So effects like these, we want to model these. So our niche is currently weather event-based multi-hazard. Okay, so we set out for an integrated approach to this type of modeling. Multi-hazard simulations, including interactions, and we try to implement everything from a fundamental level. So that means we simulate it on a physical basis using physically based equations, and then let the interactions come out of these equations. So today is a short course. Presentation is first, some theory, some applications, some questions. Then the workshop, exciting stuff. I'll talk about how you can actually get a simple simulation running right at the start. There's some pre-made data sets for you. So you'll run some test scenarios. We're going to look at altering some stuff, maybe do some exercises with it. But we'll see where it goes. You have a say in it. And this is just an example of the software. Okay, so this is the schematic view of what we wanted to achieve here. So the processes we currently have in there that are all interacting and working. So from rainfall towards full catchment hydrology, infiltration, groundwater stuff, we have the channel flow, the flooding, sediment transport, so erosion is also in there. OpenLISEM started as an erosion and hydrology model. And we added then shallow landslides, automatic volume estimation, the runout, and the runout is two-phase, so it can have water and debris and rocks and stuff, all mixing, and that interacts also in a natural way. Okay, so the hydrology stuff, yeah, same old. It's just the same, similar to others. Hydrological catchment model. OpenLISEM has been doing that since 1993. We include all the stuff from vegetation, so interception, through flow, splash attachment once the rainfall hit the ground. We have infiltration based on green and amp, and then afterwards groundwater flow is modeled. Hydrology is also influenced by urban elements, houses and buildings. Okay, so then after hydrology is solved, at the same time, every time that we look at the slope stability. So we use an adapted version of the infinite slope model. We adapted it a bit to also give us failure volumes. I'll talk a bit about that later. But in principle, the equation here is simply at a certain potential failure plane, you look at all the forces that are pushing downwards and the forces that are pushing or are resisting the downwards movement. And the one is simply the weight, and the other one is based on the Moore-Coulomb stability criterion. And we also implement, of course, the metric suction in the soil and the core pressure. So the iterative method uses these assumptions to get an estimate of the failure volume. How that works, well, read the paper for more details. I'll talk quickly about it. Basically, once we find a cell that is unstable, we inversely solve the equation and say, what depth do we need to have at this cell to get a stable situation again? So once we remove the material there, we go to step 2. We see the slope of the upslope cell has been altered. So there the force balance has been altered also. So typically what you see is this cell might become less stable. So we remove again the amount of material required to get a stable situation again. And we keep on iterating until finally we have removed the least amount of material required to get a stable slope. So the good thing about this method is that it's organically shaped according to topography. It gives us bulk releases of mass from the slope, so no sporadic pixel-sized failures. It's quite fast. We can combine it real-time with hydrology. Other methods like random ellipsoid sampling tend to be more accurate. They're more meant for rotational deep failures. This method only works for shallow failures. But however, on the other side, it does allow us to combine it in real time with a hydrological simulation with groundwater stuff. Okay, so we improved it a bit further, trying to have a more look at rotational behavior. So we added a simulation of the subsurface forces. So we do a steady state simulation of how much force is coming from upslope and pushing towards the downslope cells. So we iterate from upslope to downslope and say for each downslope cell we add the excess force that we have from its upslope neighbor, and this sort of sums up to give you a forcing towards the down part. This gives you a bit more of a realistic behavior, this type of estimation. Okay, flow equations. Basically, we start out with the Saint-Venant shallow water equations. So we have our 3 continuity equations for this. Continuity of mass, continuity of momentum in the x, and continuity of momentum in the y direction. So these work for water flow over the surface. Friction is implemented using Darcy's friction law, based on Manning's n values. Then as soon as there is a slope failure, we get a lot of solid material that enters the flow. Well, these are the momentum sources for water. So gravity is, of course, there, 9.81. Action is reaction, so we have pressure differences that are there, and friction. Manning was right in that sense. Manning's n does provide a good value for the friction law. But as soon as we get solids, there's some more forces that we put in there. So these are based on Kudasai's 2-phase generalized debris flow model, based in his paper in 2012. We made some adaptations to also get it to work with normal water flow. The additional forces that you see here is that solids can create their own stability, of course, due to their internal friction angle. We have viscosity. There's a drag force between the water and the grains that is added. And there's diffusion of small particles based on concentration gradients. What results is long equations. You don't have to bother with these. The model does it. It solves it. yeah, if you're pretty interested, we'll have a talk later. It's they're very beautiful in the mathematical sense and in what they can do. Then finally, once you have a debris flow moving downwards, you also tend to have entrainment of soil material. We also model this. You can use some different equations in there. We use the one from Takahashi, 1993. It works well for us. It's based on the excess shear stress. So this is the shear stress that the surface has. This is the critical shear stress for entrainment, which is based on the stability of the soil. And K is just an entrainment constant, which is important in calibration. There are some fully physically based equations for entrainment, mainly one from Pudusaini last year. We've implemented it, but we've seen so far that this gives us a bit more vector results. It's more stable, if you want. Okay, this is the final flowchart of the model. You put in all your data, you load the run file, LISEM sets up all the initial conditions, and it starts with a main loop doing all the processes. So LISEM allows you to turn off or on all the stuff you want. So if you want to start out with the basic stuff, you can just run the blue, the hydrology. You get precipitation, interception, infiltration and groundwater, surface storage, and water dynamics, if you want also with the channel. This is the basic setup that you run the model in. Then if you want to extend it, you can go towards sediment processes, which is meant for agricultural type erosion. So you get splash detachment, flow erosion, and this transfers through the water. And then if you want to extend it even more, you get all the solid processes like slope stabilities in there, slope failure, and then automatically it's introduced into the flow. Okay. So the software is open source, free. It uses an interface. At the moment, it works on Windows and on Linux or Mac, only if you use it in a virtual machine. If you really want to use it extensively, you should be able to run it also on those. You have to compile it yourself. All the code is written in portable C++. It's been tested by one colleague who said he could run it with not too much effort on Linux. And the dependencies are Qt for the interface, which is also portable, Boost for the multi-threading, and some other libraries, but all of those are portable. And as I said, the code is open source, so you're more than welcome to have an attempt, and then please let us know if you get it working, we'll put it online. So this is an example. This is a part of a Caribbean island, St. Lucia. We'll talk more about the example study cases later. This is just a video of how the results look like in the interface. So this is a flow height. You see hydrology flooding coming up, and you see a lot of slope failures being introduced and actually running out towards lower regions. This is the failure height at the end of the simulation, flow velocities, the actual debris flow, so the actual solid material in the flow, and this is the soil loss. It's a bit quick, let me play this again. So at the start, everything infiltrates. This is a hurricane, so it's quite a lot of rainfall, so it's a big event. You get some flooding, the slope failures are slowly added. You see here and there some shallow failures popping up. And then the runout mixes with the water or it blocks channel flow. This is the failure heights in total, the flow velocities, the actual solid material, so the debris flows itself, and this is the erosion and deposition. Just an example. And we also have a 3D viewer in there, which is very much beta. It's sort of a hobby thing I put in, so don't blame us if it doesn't work. The code is good. The 3D stuff is just a hobby thing. But it's nice to visualize, especially when you're trying to explain to people what's happening. So this is an example application that that's also in the publication that Luigi showed. So this is the Scaletta area in northeastern Sicily. It experienced, I think it was a 1 in 30 year return period event, convective storm, 2009, leading to really high density of landslides in a small area. Well, the areas, as you can see on the image, some build-up areas on the coast. The rest is mostly sparse vegetation. and the rainfall intensities are on the left. So there was quite an intense peak, more than 120 millimeters per hour intensity. So here, there was a real case of debris flooding, so we tried to model this. So the image you see here is an overlay of the debris flow, mixed with all the hydrology stuff, of course, predicted by the model. So this is fully physically based. No assumptions, no calibration, well, there was calibration, but no knowledge of the final results were input for the model. So the calibrated simulation here from hydrology where slope failure ran out everything, overlaid with the actual image on Google Maps for 1 month after the event. So yeah, we were quite happy with the results. Of course, we need to continue this and see how well we can also use this as predictive model. But we were able to capture the impact and in a sense also the behavior of the model quite well. What you also saw really was that the influence of running debris flow simulations with or without hydrology was quite intense. So here on the left you see the simulation with hydrology. So this is the maximum debris flow height. And here a debris flow is a flow with at least a concentration of 20% solids. On the right you see the same map without hydrology. So that's just the run out of the landslides. So you see the run out distance of the material is a lot more. And what we actually saw that in reality there was a huge fan of debris material near the coast. So this gave a good confirmation that indeed this multi-hazard type of modeling is important if you want to capture all aspects of such an event. Availability, I talked a bit about this open source. If you didn't have to get the USB stick yet with all the stuff, and you want to follow with what we're doing on the screen, please ask. We'll bring you the USB stick, or you can download it from the website. So, intermediate conclusion, due to the advancement in the past decades in techniques for multi-phase flow modeling, for all these land surface processes, we can make a new step towards multi-hazard simulations, and maybe even multi-hazard and risk assessment. And we see it captures new aspects of behavior that weren't available before. The actual links are here. SourceForge page is where you'll find most of the files, the application. If you're downloading it at the moment, I'll have a look at the website next slide. Or if you want to use USB stick, please raise your hand. And then, there's some example data sets in there, the program itself, and the PowerPoint is also there. But I think most of you already have it.
Right? Is there anybody else that needs a pen drive for the installation? There we go. And, you did it.
So the SourceForge page has all the code also. It's hosted on GitHub. But if you're just interested in the files, make sure you download for this section OpenLISEM Hazard, public beta. This is the one we're talking about now, the one that does the multi-hazard stuff. The regular version is mainly about flooding, hydrology, and erosion. This is what BSEM was originally built to do. So my PhD project was extending it. So the OpenLISEM Hazard version is sort of my a child. And if you download, there's two versions. The regular one features the 3D viewer. If you don't have a new graphics card or support for OpenGL 4.1, download the top version, With the top, the regular is without 3D interface. So then you don't need the graphics card and the application will still open. If you start this one and you don't have a graphics card, it will crash. So if you encounter this, know that it's easy to solve. Okay. Any questions so far? Yeah?
Can the software cope with vegetation cover? If you got trees or something, but that can hold the soil strongly.
Yes.
If it's bare soil or with vegetation, they should be different, yeah?
Yeah, so we thank you for your question. We do implement some vegetation effects. They influence, of course, the hydrological cycle there through infiltration, porosity, but also they provide some extra cohesion that you can put into the model. So it's not very extensive, but we do put in the vegetation effects for slope stability. Yeah, and also for entrainers.
Thank you.
Any other questions? Yeah.
Yeah, I wonder. So it is impressive. Let me say. So
Thank you.
It is very, very.
It's in beta.
So okay, but
after you use it, then you can judge.
I think it's challenging and something that it's the first time I see something like this. So impressive. So the problem is with the physical-based model. The problem is the calibration of the parameter. So you are coupling a lot of let's say processes that require a lot of parameter in order to be calibrated. And I wonder how were you able to obtain such similar results in Scaletta, since it is hard to calibrate all the parameter of soils, vegetation, friction of Darcy equation and stuff like this. So it's how did you get to?
Well, so this is the area of my PhD.
Yeah,
so
I know.
For this specific region, I went there and I collected information on soil depth, for example, and when you need to fit to a
geotechnical parameter is
geotechnical parameters. Well, we didn't have them, so you have to go into the literature and actually convert.
And did you take a long time it took a long time to calibrate this data to try to find the best combination, or
I think in total, I ran it maybe between 30 and 40 times to get a full scope of what the model did for various parameter combinations.
Okay.
So then I calibrated mainly for the infiltration rates, the soil depth,
which we had.
Yeah.
I went personally to.
And the internal friction angle, which was from literature. So we saw mainly soil depth model that spatially. I'll talk about that a bit later also. I'm preparing a database for the model. Soil depth is a very hard parameter to estimate spatially. You can measure some points, which I'm glad there was data for. Still, to have a spatial view of that is very hard. That's certainly something you have to calibrate, and the same with strength parameters if you take them from literature. One of the main conclusions from that, I think, we should take is that at the moment, to use it for real predictive modeling, you need to be very vocal about there is a lot of uncertainty in there because you're coupling so much. But as we state in the paper also this, like the function at the moment of this model is not to predict, especially the moment of failures. That's too hard. You don't know all the subsurface stuff, all the structural weaknesses in the soil. What instead we envision the use is to be able to recreate past behavior to understand it better, and to say we can simulate certain scenarios. So we have a variety of multi-hazard scenarios that could happen, and among these we say, okay, there's some certain things that are highlighted. Maybe there's additional risk in a certain area of the city because we notice certain behavior can occur. So we need to be very vocal towards, especially decision makers. Like, this is not reality per se. It can be, doesn't have to be. Yeah, but it's a good question. Does it help? My answer? Yeah. Okay.
I'm impressed. I see. So.
Thank you.
Last question.
Yeah.
Yes. So I was gonna ask something related to that. Did you guys did some sensitivity analysis? Which parameter affects much most, like your outcome?
Yeah, so it's not in the paper, but what we found mostly was that soil depth was very uncertain, particularly the spatial patterns. So if you take a homogeneous soil depth throughout a slope, that doesn't work well because your bottom areas are way too stable. Typically, soil tends to accumulate there. Your top areas are way too unstable because at those very steep areas on the high end, it doesn't have the capacity to carry that much soil. That was, I think, the most important one, and after that, I think the internal friction angle, and then the infiltration rates. But very short maybe.
Yes, we need to move on to the application. So,
how do you get from slope including slope model so in 2D to a 3D volume?
Oh well, it's quite straightforward to extend this to a 3D thing. So instead of checking the upslope cell, we just check all the 9 neighbors, And the slope for one specific cell is defined as the slope towards its steepest downslope later. So yeah, we just extended this basically towards two directions.
How do you define the profile? You're doing that. On the previous slide, the model, it's on a profile. Or is it when you extend it to 3D directly?
You mean this one?
Yeah.
Well, yeah, you can simply solve the equations in 2 dimensions. But maybe we should discuss this afterwards. Yeah. That's. I'll keep this in mind. I'll come back on it. Yeah. For you, last question maybe.
Yes, so the parameter of friction between bedrock and the soil. Can you change its area, the area? Does it have a variability of this friction parameters?
How do you mean? You mean like the internal friction angle of the material, or?
So the friction between bedrock and the soil.
Oh yes, yeah. Well, in principle, we assume that in our soil, every potential plane that you can envision in between the top and the bedrock is a potential failure plane, and the friction that we use at those planes is always the same. So we do not treat the bedrock interface as a very special case in that sense. Yeah. Which is maybe something we should include. So if you have ideas about how to.
Yes, on the tube we especially look for the interface between soil and bedrock to predict possible failures.
Mm-hmm.
So this will be very interesting for us to implement it to model, for example, these situations.
Yeah. Well, yeah. We initially also we started out. Well, if you use the infinite slope model, typically, you have only one potential failure plane, which is the bedrock interface with the soil. But we felt in this case, we saw there was a lot of shallow landslides, and if you use that model, you got a very binary pattern. So it was either everything or nothing, which got a bit weird results. So with this method, it doesn't necessarily follow either the bedrock interface or there's no failure at all, but you do get more of the ellipsoid organic shapes that you would see in reality. Yeah. But we can discuss this later, maybe. Yeah. Okay. So far for the theory. Are you guys ready to get some hands-on stuff going? I hear enthusiastic voices. No, maybe not, but you're here, so we'll do it anyway. Part 2, using OpenLISEM. Let's have a look. So I'll talk a bit about model setup and how to run the example dataset. In the coming 10 slides, I hope to see everybody with a screen that has the simulation at least running. That's my goal here. Short-term goals, that's good. Okay, first a bit of requirements. Typically in our workflow, what we use for data preparation, Excel, spreadsheets, no new thing there. ArcGIS or QGIS. I prefer QGIS. One reason it's more streamlined in the use of GDAL. GDAL is the map reading library that a lot of GIS software use. GDAL has built-in support for the PC raster map format, which is the map format that we use by default. You don't have to use it. You can import and export geotips into LISEM or any other format that GDAL supports. However, typically we do our data preparation in a free GIS called PC raster, and QGIS has built-in support for PC raster maps.